Hello, everybody. Welcome back to my basement. It's a little louder down here than usual today because we're getting a new roof put on as I record this, so I apologize if any of that extra noise shows up on the recording. So the first 20 minutes of class yesterday on October 29th were all that were somehow captured between the stream and my recording. I apologize for that, but I am here today to try and fill in what we covered after that point. So I am starting from page 3 of example 4. This is the model in which we are going to be predicting annual income as an quantitative outcome variable. And we're starting with an empty model, and then we're going to work through a series of three actually, alternative models that include predictors, each of which has more than one slope necessary to fully describe its effect. So empty model is our first step here. This is something that I use for pedagogical purposes. One wouldn't necessarily need to estimate this in practice because the results of the model are going to be inferred based on the models that follow. But for demonstration purposes, I want to make a point. The empty model has a fixed intercept in it. That means our best guess for what each person's outcome variable is going to be, which is income here in thousands of dollars, is just going to be the sample mean of income. And the E residual for each person, that tells us how far off each person's real income is from the one that's predicted just by beta 0. The variance of those E's across people is our residual variance, which at this point, in the absence of predictors, means we have all of the variance in income yet to be predicted. So said differently, the total variability in our outcome variable is 190. The R square is exactly 0, meaning that we have not yet accounted for any of the reasons why people have different income levels. They are all still up for grabs. So the residual variance is as high as it is going to be. We have not accounted for any of it, and that is why R square is 0. So from here, what we should see is that our mean square error term, which is our residual variance, should decrease. There should be less unexplained variability as we add predictors to the model. And the proportion by which it decreases is going to be given to us as the R square. So the R square is a tally of what proportion of variability has been explained by the model predictors. So without any model predictors, our best guess for what each person's income level is going to be is just the fixed intercept, which takes on the sample mean. And just as an FYI, that is also shown in the SAS output right here. So then we looked at adding a predictor for self-reported working class. So this is a categorical variable. You might call it ordinal, but these are definitely not numbers, where people could choose whether they viewed themselves as lower class, middle class, or upper class. Then we created two new predictors to represent those three groups. So given that we have three groups to represent, we're going to need two predictors to distinguish the three group means. We create those predictors by first creating empty columns and then populating those columns with zeros and ones that correspond to what we want the predictor variables to mean. So the group that is to be our reference gets 0 values in each of its predictors, so that's working class number 1. And then for each of the other groups that we want to compare to the reference group, we turn on the predictor by setting its value to 1. So L versus M is intended to capture the difference between the low group and the middle group, so that's why the middle group gets a 1. Likewise, L versus U is intended to capture the difference between the low group to the upper group, and so it gets a 1 here. The same thing happens in Stata, except that the conditional part is last in each of the statements, and the value to be replaced is given first. So then we put those two new predictor variables that are 0, 1 coded, dummy coded as it's known, or reference coded, into the model. And here is the logic by which the model then creates each of the group's predicted means by filling in the model parameters and the values for the predictors that correspond to each group's membership, so the same combinations of zeros and ones by which we created the variables. And then this part shows how all three group differences are then given by the model parameters. So the differences relative to the low group are given directly by the two slopes. The differences between the non-reference groups, so in this case middle versus upper, is given to us by the difference in slopes. And you can follow the logic of this by substituting in how the model gives us the mean of each group, and therefore how the model gives us the mean differences by literally subtracting the means to be compared. So then we have the two slopes going into the model to distinguish our three groups. Estimate statements are asking for what the group-specific means are going to be. Note that the first one is given just by the intercept, and so we don't technically need it, but it's here for pedagogical purposes. We would want to know what the other two group means are because those are obtained as linear combinations of the model fixed effects. Likewise, these two group mean differences are already given by the model's slopes directly, whereas the third is a linear combination that is not yet given directly, so we want to ask for that. So that is to say, these three statements right here, the middle and upper group means and their difference, these are all given to us by model implied effects, linear combinations of the fixed effects that we are asking for via these estimate statements. And in Stata, we do the same with these lincom statements right here. Then we get to the results. So the table of sums of squares that we started talking about in class, let me go back over that. So what we are looking at is how much information this three-group predictor variable has captured, has accounted for, has predicted in the outcome relative to how much information is still unexplained, is left over, is not related to working class. So we want to be able to develop a ratio of those two sources of information. So we have sums of squares for the model. That is how far off each person's predicted outcome from the model minus the mean. So how much more information have we introduced by adding the predictors relative to just guessing everybody at the same value of the mean? And then how many slopes did it take to provide that model predicted information? So degrees of freedom for the model is the same thing as what's known as degrees of freedom numerator. So if we take sums of squares, divide by the number of slopes it took to obtain that level of sums of squares information, we get this thing mean square. So this mean square model is how much information the model captured per slope it took to get there. Then how much is left? That is given to us by sums of squares for the error, or sums of squares residual as I call it. And this is how much information we don't know yet. So it's each case's outcome minus the outcome that is predicted by the model. So y sub I minus y hat sub I squared and summed over persons. So that's all of the reasons why people deviate from the model predicted outcome. And how many more slopes could we add is a function of sample size minus the number of slopes we've already spent. So in this sample, there's 734 people. Degrees of freedom for the error, which is known as degrees of freedom denominator, is n minus k, so 734 minus the three fixed effects that we have in our model. The three fixed effects that we have in our model are the fixed intercept and the two slopes. So that's where we get 731 more slopes we could have added. So the amount of information we don't know yet divided by the number of slopes that we could have added gives us this magical term right here, mean square error or mean square residual, otherwise known as residual variance. So this is the amount of variability yet to be explained in income. So this is leftover, unexplained, unaccounted for variability. And to try and distinguish whether or not our model has done a good enough job in predicting the outcome with the slopes we've included, we take the mean square model, divide it by the mean square residual, so a ratio of what we know in the numerator to what we don't yet know in the denominator, and that ratio is our F test statistic. So this F value is a ratio of what we know over what we don't, each quantity weighted by what it took to know it. Number of slopes spent in the numerator, number of slopes could have spent in the denominator. And this p-value references the F distribution that corresponds to our numerator degrees of freedom and our denominator degrees of freedom, and it gives us the exact p-value of the current F value that we found for the model relative to that reference distribution. So the same rules apply. What F is telling us is how likely it would be to find slopes as big as we found if both slopes were zero, the null hypothesis was true in the population. So less than 0.01% of the time, we would find a model that accounted for this much information if the slopes were actually zero. How much information did we get? Effect size that goes with that F test statistic is our R-square value, and R-square is about 0.10. In other words, 10%. So of all of the reasons why some people make more money than others, 10% of those reasons are attributed to their self-reported working class, whether they responded as low, middle, or upper. So 90% of the information is left over. In other words, if we go back to our empty model, 190 is all of the variance that there is to be had in income. We still have 171 left, and that is a reduction of about 10%. So you can think of R-square as the proportion of variance accounted for by the model. It is an effect size that corresponds to this F-test for the model as our two slopes. And we can also think of R-square as the correlation between the y-hat that is predicted by the model and the real y that each person has. If you take that correlation and square it, you get R-square. And this reporting format, you will get a chance to practice in your homework because this is a universal way of talking about these results. So I've put in bold font the numbers that show up in this reporting format. The reason why we report mean square error or residual variance specifically, along with the quantities related to F, is because that gives us enough information if we wanted to be able to fully reproduce this table. And then in terms of what happened, the intercept, our beta 0, directly gives us the mean for the low group. Each of our slopes tells us how different the other groups are relative to low. So the middle group is different by 8 relative to low. The upper group is different by about 11. And the difference between those two slopes gives us the difference between the middle and upper groups. So that difference of about 2 is a model implied difference that we asked for down here. So these are our estimate statements that give us the extra pieces of information we might want to know. And then we talked about this before. The idea of the general linear model is based on the residuals for the model. So the e's that are left over, which have a histogram right here and a QQ plot right here, they're supposed to be independent across persons, they're supposed to be normally distributed, and they're supposed to have constant variance. And the normality assumption is a little sketchy. It's not terrible, but perhaps another type of model might be more appropriate for these data. Come back to my other classes if you want to learn about some more options for that. Likewise, if you want to talk about heterogeneity of variance, come back to another class. So in terms of effect size, these coefficients for the group differences are scaled in thousands of dollars. If we wanted to put them into a metric that has an absolute range that everyone understands, such as an R metric that goes from -1 to 1, we can ask for standardized slopes. To do that, we need to switch from proc-GLM to proc-reg if we're using SAS, add the STB option to the model line. By the way, the reason that we're not using proc-reg more generally is because it doesn't allow estimate statements. So proc-GLM doesn't give standardized slopes, but it does have estimate statements. Proc-reg does give standardized slopes, but it doesn't have estimate statements. Likewise, in Stata, adding the option beta after the comma in regress gives you standardized slopes, But in doing so, it removes the confidence intervals for the unstandardized slopes. So we'd have to run it twice to get all pieces of information. The new information that is provided after adding this beta sub option in Stata or the STB standardized option in SAS is an adjusted R-square that is printed in SAS proc reg, so that's the one that's corrected for sample size, as well as the last column in the parameter estimates table, which gives the standardized slopes. So these are effect sizes in a correlation metric for how big the difference is between the low and medium groups and between the low and upper groups. When we're talking about group differences, effect sizes in a correlation metric can be less intuitive than an alternative, which is known as Cohen's d. Cohen's d gives you a group mean difference in standard deviation units. I am computing Cohen's d in SAS by saving the results from this table. So I asked SAS to save the results from this table that came from my estimate statements. That's what ODS output does. It saves the results to SAS datasets so that you can do math on them. There is a way to do it in Stata, and I spent a few hours trying to figure out how, and I was unsuccessful. So I don't have an example of how to do that in Stata. But once you have the results saved into a data set, you can then compute Cohen's d. The formula for it is right here, and that shows up as the last column in this piece of printed output. So in other words, the difference between the low and middle group is about 0.65 standard deviations. The difference between low and upper is 0.27 standard deviations, and the difference between middle and upper is about 0.05 standard deviations, so quite a small effect. And here's some words to describe these findings. So then we moved on to talk about how to include nonlinear effects of quantitative variables. So we're looking at age as a potential predictor of income, and always starting by examining the descriptive statistics for the variables to be included. Age in this case, we're using proc mean since it's a quantitative variable to summarize its mean, standard deviation, and so forth. The analog in Stata is the command summarize. And here's the information for the variable. The mean for age is about 42. The standard deviation of 13 tells us that the average person is off from that mean of 42 years by about 13 years. And the sample age ranges from 18 to 25, or 18 to 75, excuse me. I am going to center age at 18 for this example. I picked that and thinking about an 18-year-old as my reference group, and then what happens to their predicted income as age increases. I have a picture of what age looks like here, and I also made an extra plot. Code is available for how I made this online if you want to know, but what this plot is showing is the mean income per 2 years of age. So I temporarily rounded age into 2-year increments so that we could look at the means per age. And the black line conveys the means, and the red lines around it convey the standard errors. So what we see here is definitely not a linear pattern. This is sort of a classic shape known either as a quadratic pattern or a parabola, where it looks like there is a linear positive relationship with age that begins to slow down and eventually change directions as we get older. So based on this, I am going to fit not only a linear effect of age as a starting point, but I'm also going to test whether or not a quadratic effect of age makes the fit better. First step, create my new predictor variable. So I am doing so right here in SAS and right here in Stata. The variable before the equal sign is the new one to be created. So that needs to be a new name that you assign. My convention in labeling variables is to put the centering constant at the end of the name. So that's why I'm calling this new column age 18. After the keyword gen in Stata, same thing. And then after the equal sign is how the new variable is to be created. So the age here is the variable that already exists in the data set. So you would need to know what the column is already called and then describe the mathematical operation by which you want to create the new variable. So I have my original column named age minus 18 gives me the new column, which I have named age 18. So let's see what happens when we put that in the model. So I've taken out working class for right now, and I have included a linear effective age, and the centering constant is shown in the equation so that you know what the reference group is. So beta 0 is going to be the expected income for an 18-year-old specifically, and beta 1, the slope, is going to tell us how income is expected to change as age increases from 18. I have demonstrated some estimate statements and some LINCOM statements in Stata that are generating model predicted outcome values for other cases besides the reference. So even though beta 0 is referring to an 18-year-old specifically, this model gives us what income is predicted to be at any age. So as an example, I've asked her what income is expected to be at age 30, 50, and 70. And note that those real ages correspond to centered ages of 12, 32, and 52. In other words, age 30 is 12 higher than the centering point of 18. So that's why it's 12, 32, and 52 that go into the equations, because it's relative to the centered version of age. So there will be some extra output generated from these requests. This is not something you need to do in homework 4, by the way. It'll be enough just to fit the model. So here's our results. We're only looking at a linear effective age, so one slope. So this is an instance in which the information that is given to us by this table, referring to the level of prediction captured by the model, is one and the same as the information given to us just for the slope of age. That is, if I took this t value down here of 5.52, which is the test statistic testing this slope against a null hypothesis of 0, so our obtained slope is about 5.5 standard errors away from the null of 0. If I took that t of 5.5 and squared it, that would become this f value of 30. So when you only have one slope, the f-test for the effect of that slope in the model is the same thing as the t-test for the effect of the slope, because the one slope is the model. So in this case, including that one slope reduced our error variance from 190 down to 182, which is a 4% reduction as given by the R-square. The coefficient for age is positive, so the model predicts that for every year older you are, your predicted income goes up by 0.2, so $200 in this scale. And this is a linear effect. So this suggests, if this model is correct, that if you want to be rich, all you got to do is get older. Just wait. Your time will come if you hang in there. So this seems a little improbable that income would continue to increase at the same rate indefinitely as one ages. It's also inconsistent with the plot of the means that we looked at earlier, where it suggests that income is positively related to age up to a point, and then after that it's negatively related. So to be able to capture this curvature, this bendy sort of regression line, we're going to add in a second slope to our model, which is age squared. So age 18 squared is the second term. That is going to be able to create that U shape that the plot of the mean suggested would be a better way of representing the effective age. So it takes two slopes. We are leaving in the linear slope for age, and we're adding the squared term to represent the quadratic slope. So these two terms are going to work together. You can only interpret the quadratic slope as quadratic if the linear slope is also included. So quadratic is above and beyond linear because they are hierarchical terms. in ProcGLM and in Regress, you don't actually have to define the quadratic variable ahead of time. You can do so on the fly. And in SAS, the way that you do so is with an asterisk. That creates more generally an interaction term. So we're creating a predictor that is a multiplicative combination of these two variables. So star creates a squared term or an interaction term more generally. And in Stata, the same thing happens if you add this symbol, which has two different names depending on your cohort. So I would say for those of us who are over 40, this symbol in Stata is known as a pound sign. And for those of you who are under 40, this symbol I would say is a hashtag. So whichever you call it, that symbol allows you to create a multiplicative combination of two variables, either for an interaction term more generally or as a squared term in this instance. And note the C dot in front of each of the predictor names is necessary to tell Stata to be able to do math with it. So all you need to worry about in your homework is adding these two effects to the model as predictors. You do not need to worry about any of these other estimate statements. These are here to demonstrate how you can ask for model predicted outcomes as the first three lines here. So note that the same ages are being used as an example of how to ask for a predicted outcome at particular ages. And we've added the squared term to the model with values that correspond to the square of the ages being entered. So the 12 here, because age 30 is 12 years more than the centering point of age 18. If we square that, we get 144, and squaring 32 or 52 gives us these values as well. These three lines are giving us the model predicted linear age slopes at particular ages. So in physics terms, these are known as the instantaneous slopes. They are the slope of the line that is tangent to the curve at these particular ages. The model is directly going to give us the expected linear slope at age 18 specifically because that's where age is centered. But you can ask for what the slope would be for linear age at any other point. And the trick to doing that is to multiply the age you want it at times 2. So let's see what happened. So we have a model now with two slopes in it, meaning that we need to look at the overall test of the model as well as the test of each individual slope. So age and age squared have captured this much information divided by the two slopes it took to get that much information gives us our mean square for the model. There is this much information yet to be captured divided by the number of slopes that we could have added gives us our mean square residual or mean square error term, otherwise known as residual variance. So this is the amount of variability unexplained by the model relative to the empty model of 190 having 168 left gives us a reduction of about 11%. So 11% of all the reasons why some people make more money than others has to do with age and age squared. And the F value for that R-square is significant, indicating that the reduction in variance is significant. So this R-square is greater than 0 significantly. Or you can think of the y hat that is predicted by age and age squared is significantly correlated with the real y for the outcome variable. The interpretation of these parameters is similar with respect to the intercept. So because age is centered at 18, the intercept gives us the expected income for someone who is 18 years old, and that is about $2,600. This linear slope is no longer just the linear slope of age. It is specific. It is conditional on where age is centered because of this higher order term. So this slope of age is specific to age 18. It is the slope of the line at that point on the curve specifically. So at age 18, for every year older you are, your income is predicted to go up significantly, given the p-value, by about $1,200. However, the slope that says income increases as you get older, that positive slope is going to be made less positive. So the terms of the linear and age slopes are working against each other in this case. So I would say that the effective age is becoming less positive as age increases. And the trick to interpreting a quadratic coefficient correctly is to remember to multiply it by 2. So for every year older, the linear slope of 1.22 becomes less positive by twice this quadratic coefficient. So the quadratic coefficient is 0.02, so it looks like for every year older, the slope for age becomes less positive by 0.04. So that's how we get, actually, let me show you what it looks like in the predicted model. The blue picture over here, this shows what the model predicts the effective age to be. So the effective age 18, the linear slope, is a line right out here where x is 0. The slope is significantly positive. But what happens is that the slope of the line becomes less positive and eventually becomes negative. And you can figure out the point at which the slope is 0, and it works out to be around age 48 in this example. So yay for those of us who are middle-aged. So one last thing that we talked about in terms of this output. If we compare the R-square for this model, so age and age squared work together to account for 11% of the variability in income. This f-test tells us that that 11% is greater than 0. Relative to the previous model that had only a linear effective age, a linear effective age only captured 4%, which was also significant according to its f-test. So what we know is that 4% of the variance accounted for is significantly greater than 0, and we know that 11% of the variance is significantly greater than 0. So the question is, what about the difference between the two? R-square increased in the linear age model from 0.04 to linear plus quadratic being 0.11. So the increase in the R-square I calculated by hand as 0.074. Is that increase itself significant? And we do know that because the only difference between the model that gave us 4% and the model that gave us 11% is this single slope right here. So if that new slope is significant, we know that the change in R-square that resulted after including it is significant as well. It's a one-to-one correspondence. So because this quadratic slope that made the linear and quadratic models different is significant, the change in the R-square between models is also significant. So it looks like this is a better description of the effective age. And here are the predicted quantities I asked for in terms of what income is predicted to be at each age, as well as what the slope is predicted to be. So these latter three terms are slopes at different ages. So we know at age 18, which is when the x-axis is 0, that this slope out here was 1.22. If we go over to age 30, which would be around here, this slope is 0.75. If we go over to age 50, we are out here, the slope has rounded the turn, so to speak. It has gone all the way down to 0 and heading into negative territory. And then if we follow this curve out to age 70, which would be 52 on the x-axis, the slope at this point is negative 0.8, the value given here. So you can use estimate statements to get what the model implies the linear slope to be at any point along this curve. The one that is given to you specifically by the model is when the predictor is coded 0, which in this case is age 18. And the same problems with residuals appear relative to what we saw before. Still not quite normal, still some heterogeneity as a function of predicted income. And here's some words to describe everything that I just said. Where are we at in the recording here? 35 minutes. Okay. I believe that we also covered a few of the slides looking at the same thing. So talking about quadratic terms more generally, I'm going to start in lecture 4 on slide 22. So the general topic of this set of lecture and example notes is the idea of how do you add the effect of a predictor into a model when it takes more than one slope to fully describe the effect of that single predictor. So one instance that we saw before is for grouping variables. If we have 3 groups, it takes 2 slopes to differentiate those 3 groups. If we had 4 groups, it would take 3 slopes to differentiate those 4 groups. Another instance in which it would take more than one slope potentially to describe the full effect of a single predictor is when that effect is nonlinear. So for instance, curvilinear slopes, we just looked at quadratic. You can also fit a linear effect of a variable that has been log transformed to create something that looks like an exponential curve. That takes only a single slope, but you can also speed that up or slow it down by adding quadratic terms. We'll look at piecewise slopes next, and then there's another example in here looking at how to fit the effect of an ordinal predictor in a way that allows you to test whether or not a single linear slope would have been sufficient. So for quantitative predictors then that have nonlinear effects, what we just looked at is an example of a quadratic model or a U-shaped trajectory. So we build this by entering a linear effect of the predictor as well as a quadratic effect. And this type of model is ideal for predictors whose effects seem to change directions. If you have the effect of a predictor that sort of levels off instead, so you get to the point where more doesn't help or less doesn't help, that type of relationship, an exponential relationship, can be approximated by tricking the model into fitting it. You can do so by taking the natural log transformation of the predictor, so the logged version of x, for instance, and if you fit a linear slope to that, it will actually look like an exponential curve. So I've got some pictures to show you what that one looks like as well. So just to start with quadratic, the rule here is that in order to describe the quadratic slope as how it changes the linear slope, you must multiply it by 2. The actual quadratic coefficient that's given by the model is half the rate of acceleration or deceleration. And there are a couple different ways that I can explain this. One of the ways is by referring to taking the first and second derivatives of the function with respect to x. In the rules of differentiation, say if we're going to differentiate with respect to x, the exponent related to that thing that we're differentiating by comes down to the front. So the 2 comes down, and that's where the times 2 comes from. If you don't like that explanation, that's okay. You can just take my word for it because I said so. So I'm a mom. I have incorporated because I said so into my vocabulary. It comes in handy at times like these. We can also understand this more generally because of the way that interaction terms work, and that's something that we will get to later in the semester. So here's an example of the 4 different types of quadratic effects that you would find in data. There are only 4. It makes it easier to describe it once you figure out which of the 4 you have. A quadratic effect either takes a positive linear slope and makes it more positive, so that's the top left, or it takes a positive linear slope and makes it less positive, that is the top right. It can take a negative linear slope and make it less negative, that's the bottom left here. or it can take a negative linear slope and make it more negative for the bottom right. So in these pictures, the linear slope for the predictor, which is time in these pictures, is given where time equals 0 specifically. So the linear slope for time is conditional on the centering point, 0. And the way that the linear slope changes is by twice the quadratic for each subsequent unit on the time predictor. So for instance, if the linear slope for time at time 0 specifically is 4, and the model has a positive quadratic coefficient of 0.3, then 1 unit further along x means that the linear slope of 4 becomes more positive by twice the quadratic coefficient, so it's going to be 4.6 at 1. More positive again by twice the quadratic coefficient for the next increment, and so on. So two positives create an accelerating curve, something like number of COVID cases currently that continues to accelerate despite my best efforts and those of many of you. You can also have the slopes work in opposition. So the top right picture has the same positive linear slope of 4 at the beginning, but if you pair that with a negative quadratic, then that positive linear slope slows down as x increases. So the positive slope of 4 at time 0 becomes less positive by twice the quadratic. So this is what it looks like if rate of improvement were to level off. So people talk about flattening the curve, the rate at which new cases are detected each day. We want to see that curve flatten. This is what it should hopefully look like in the future. The bottom pictures are the same general ideas, but starting from the point of a decline. And so the left picture again has linear and quadratic slopes that are working in opposition. So a negative linear slope paired with a positive quadratic slope means that the decline that is shown here, so the negative slope becomes less negative. So this is decline that abates. A practiced effect, for instance, the speed with which you can do something increases. So if the y-axis here were something like response time, the more practice that you get, then the time that it takes you to complete something should continue to decrease like this. And last but not least, if it's negative, negative, that is an accelerating negative decline. Something like if you have a disease trajectory where you keep getting worse faster, that's what this would look like. So the negative linear slope becomes more negative by twice the quadratic at each subsequent value of x. So those are some examples of quadratic. If you come back to the longitudinal class, you'll get to see this slide again and look in more detail at this type of trajectory. So in our example, this is the type of trajectory that we were trying to fit. So a positive effective age up to some point where it switches directions. So sort of a classic parabola or upside down U shape. So then we looked at the code to be able to fit this type of model. And here are some of the results that we saw in SAS and in Stata. And here is the fit of the model through the means. Looks pretty good in this case. By the way, if you wanted to create an exponential curve, so if you have an effect that levels off, so to speak, then if you take the logged version of a predictor and fit a linear effect of it, for instance, this black line right here, if we have original time, this is approximating an exponential curve. If we change the x-axis to the logged version of time that actually went into the model, it would be a straight line. So a linear effect of a log transform variable creates this exponential type curve right here. And if you were to add a quadratic effect, so log times squared, you could either slow that curve down more or less. And so you can create a lot of flexible shapes that still fall within the family of linear models by playing around with squared terms and log terms. And so the next thing that we'll get to talk about next week then will be describing nonlinear functions that look like they should be characterized by multiple slopes, such as this one for how education predicts income in sort of different sections. Before grade 11, getting a high school degree, and then a different trajectory for those who have at least finished high school. So that is where we will leave off. I hope to see everyone next week. Thanks for watching and get the merch.